Okay, so we did a little Kahoot all about nomenclature. Now we're on into chapter 3, and we begin with mass spectrometry, referred to as a mass spec. Analytical chemist's favorite tool. Natural products chemists love these things as well because they're very effective at helping us to identify complex molecules on the basis of the mass that the original molecule had, as well as the mass of fragments that come from that molecule when bombarded by electrons. Basic outline of this device is as follows. We have a sample coming in down here at the bottom. But that sample, well, it has to be a gas, which can be damaging to your molecules if they're very complicated. They are bombarded with electrons to convert them from their normal state of a gas now into a state called a plasma. But the molecules are still roughly intact. They just have a bit of a charge associated with them. The charge is going to be positive because the electron beam that we're focusing on them is too energetic for the electron to be trapped in the molecule, so it kicks out electrons, creating positively charged ions. And those positively charged ions then, here's our ionizing filament here. Our sample is coming in this way, so the electrons are going from here to here, and they're kicking out other electrons from the sample being collected on this side of that chamber. So once they've acquired some positive charge, we can now accelerate them. We want to focus them so that we have the narrowest beam possible, because as they enter this magnetic field, the smaller, lower mass our particle has with its one positive charge, the more tightly it curves. The greater the mass, the less likely that thing is to curve off. And so we've separated large molecular weights from smaller molecular weights on the virtue of the effect that this magnetic field has. Once we've separated our molecular ions, we can use a collector here to detect them. This Faraday collector, as it's mentioned here, is simply a device that once it's been hit by a charged particle coming in, it sends off a signal, an electrical signal, which can be amplified and then sent off to a detector. So sample in, electrons knocked off that sample, accelerating the beam. Magnetic field causes a curvature of those positively charged particles in their motion. They're now separated, and we can detect them. These devices can be as large as a room. And over here, you have the small oven electron trap. This chamber is being represented by this large canister that we have here. So what we're going to do is we're going to inject our sample into this port right here. This is going to do all the heating. Here's our electron trap, but our sample actually comes out here and passes into the magnetic beam for focusing, and then into the magnetic beam, which causes the curvature. Over on this side, we have our detector and the little Faraday cage that's detecting those charged particles coming in. And of course, everything is hooked up to a computer to control the temperature at which our sample is vaporized and ionized, our other computer to detect those particles that are actually coming in. So that's what a mass spec looks like. They're pretty cool, and at $100,000, you could own your own. Now, this is what our textbook is trying to communicate to us about all of that. Slightly simplified version, which is very helpful, I think. We have a sample coming in. They've colored the beam blue simply to keep track of that. Now they're calling this the electron beam, but this is where we're hitting our sample with electrons, which knock electrons away from those molecules that we have inside. Now those molecules have positive charge, and they're accelerated by positive charge on this plate, negative charge on this plate, so moving faster as they go through this region. Now that our beam has been accelerated, moving at a high velocity, a magnetic field will alter the trajectory of our particles. These are the less massive particles because they're curving more. These are the more massive particles because they're curving less. Our detector plate is made very simplified here, but you can see that if this sample coming in were run through this, we have 1, 2, 3, 4, 5, 6, what I would call molecular ions. But what our textbook is focusing on is that these are in fact 6 different isotopes. Isotopes are atoms whose neutron number changes from one to the next, but whose proton number, the atomic number, is the same. And so for a sample of a particular element, here we're showing that there are 6 isotopes. When we go to take a look at ptable.com, we'll realize that some elements have many more than 6 isotopes. But nevertheless, our first problem that we're introduced to has only 4 isotopes. We're going to be calculating an average atomic mass. That's what we see in the periodic table. We'll be able to identify the element because the atomic mass that we calculate will be the atomic mass of something in the periodic table. We have to be careful that this is a mass and not the number of protons, so it's not the atomic number that we're going to be looking at. Now, I want to throw a curve at you because we can do this problem without a calculator. With a calculator, we'll be very accurate. Without a calculator, I want to see if you can follow along with me. Let's give this a try then. Okay. Here, I don't like that one. I'm gonna try that again. Whoa. Here, try the vanishing pen. Oh yeah, this vanishing pen. Okay. All right. What I'm circling here are what I would call the minor isotopes. So let's focus on this one first. All right. That says 208, if you follow with me. And so atomic mass units for that. Okay. Now, the other minor isotopes, I'm going to ignore this one completely. At 1%, it's making very little contribution to what we're up to here. So I'm going to take and assume that these are each 25% of my sample. And so when I go to average those, I'm looking at something that's like 206.5. Okay, now do we see then that there's a gap between these of 1.5 AMU? All right, so because this represents 50% roughly, and this represents 50% very roughly, I'm going to take this number and I'm going to divide it by 2. Okay. And so when I go to divide my, well, I'll just do it this way. 1.5 divided by 2 equals 0.75. Oh my goodness. 1.5 divided by 2 equals 0.75. So halfway between 206.5 and 208, I need to add this 0.75 to get there. 206.5 plus 0.75 is equal to 207.25. That's my best guess as to the atomic weight of this particular element. If we go to the periodic table, we might find that there is an element that matches that. But notice that I did this in my head. And you might be asked to do this without a calculator on a certain section in the AP exam. So I want you comfortable with looking at numbers, throwing out small percentages, focusing on big percentages, and making some approximations based on the numbers that you see. So again, 25%, 25%, 50%, and this would be the atomic mass we would anticipate. Let's see if that is borne out by a more complex way to approach the problem. That is to say, using a little spreadsheet calculation to do this. And so what I've done here is to write those percentages out. Here's the isotopic mass as given in the problem. And this contribution simply represents the product of percent times isotopic mass and then I've written it this way. You have to be very careful here that I converted this percent into a fraction. So in other words, this is not 1.4 times 203. This is 1.4 divided by 100 times 203.97, and so on. And so notice that our more accurate estimate for this atomic weight isn't far off, that our previous estimate differs in the hundredths place, down at the point where our uncertainty lies, because we can only have 2 digits after the decimal point in the way we've manipulated these numbers. To be very brief on that, I have 3 sig figs here, 3 sig figs. I chop off right here, so I have 2 digits after the decimal point. Here I have 4, so 1, 2, 3, 4. Oh, good, to 2 digits after the decimal point as well. Here I have 4 sig figs. Here I have many more than 4 sig figs. 4 sig figs. 4, many more, 4. So in each case, I lied. 4 sig figs here, I have to chop this off right here. So in fact, it's 1 digit after the decimal point, and that makes our approximation that much better than what we saw there. Nevertheless, if we go to look at the periodic table, we will find that lead has an atomic weight of roughly 207.2. And so we've been able to answer that question in just that way. These are very typical questions where we have graphs. The College Board likes you to be able to interpret graphs. And this is the result that would come straight from a mass spectrometer, where we would have a bump at 63, another bump at 65. The height and width of that bump at 63 would be greater than the height and width of that at 65. We integrate under those curves to come up with how much of each isotope of copper are present there. Since we've got roughly 70% of the less massive and 30% of the more massive, our average of these two is going to be skewed in favor of this 63. So we're going to be somewhere around 63.5 or 63 and 3 2/3, somewhere around there. But if we now do this very accurately, we're converting these 69 and 30s into fractions rather than percentages. And we do the same multiplication that we did previously. And now we show that copper weighs on the average about 63.55. And our periodic table agrees with that. So these are isotopes. Many elements have more than 2 isotopes. The College Board is interested in your ability to handle exactly two isotopes. Love the animation, what the heck. Now, this is the point at which I'm going to stop this video, and in class, we will start with this little activity. Isotopic pennies, okay? I'm going to hand you a taped up set of 10 pennies. You are not allowed to open up that tape or take a look at the pennies that are inside. What I can tell you is that wrapped up in each of these pieces of tape, you have exactly 10 pennies. Just like any element in the periodic table, there are isotopes of that particular element. So what I'm asking you to do is to determine for your particular element how many are heavy and how many are light based on the analysis that we've done previously. But this time you have unknowns rather than just plugging and chugging on a calculator, multiplying and adding as you go. Now, I would also like you to understand that something happened in 1983 to pennies. If you go to Wikipedia and look up pennies, you'll get a very interesting story of what's going on there. Take a quick look at that. Don't spend more than 5 minutes on that. That's fine. Okay, 10 pennies. How many light ones? How many heavy ones do you have? Mass of the tape is on average 0.242 grams. Weigh your sample, and you're going to figure out how many of each type in your element. We do this in honors chemistry with far less setup. And so don't tell your chemistry honors friends what we did in AP chemistry. They'll be all jealous. So this particular video stops here. We've dealt with isotopes, and we've introduced what a mass spectrometer is and what it does.